new algorithm to tackle with the root cause analysis of BGP analysis of anomaly in BGP. So this is a joint work with Anthony Lambert and Jean-Luc Luton. Anthony Lambert should have presented this work, but I do it for him. Okay, so as so many people know, any event localized in an AS can raise updates all over the BGP network. And we believe a tool that will detect and also localize those events can be very useful to help network operation center during outage, and also to detect some small recurrent events that can arrive many times. And we also think it could be useful to detect some peer or some AS that are not reliable. Okay, so the principles is to collect some BGP updates at multiple vantage points, and then to identify events and to localize responsible AS for those events. In fact, so there is 2 steps in these methods. First, we've got to decompose the stream of updates and to clusterize those updates into sets, and the sets would represent one event, and then given any event, we have to localize the responsible for this event. Okay, so there are many challenges in such an algorithm. First, we've got only some lessons echoes of the events, because the BGP updates are spread all over the network, and we only got some data from a few monitoring points. I mean public monitoring points like root views or RICE. Okay, so and the effects of those events are spread over time because of timers, for example. So this is vendor specific. And if the effects of those events can be very spread over time. So as we will see in many previous work, they thought many updates generated by the same event can happen close in time. So it is usually true, but not always. And finally, one of the issues of this work is that the data is strongly biased. I mean, when we monitor at vantage points, we usually see the topological, AS path near the monitoring points than spread over the network. Okay, so main ideas in the previous approach was to use timers to identify BGP updates related to the same events. So they could also use some kind of aggregation. And then to tackle the localization of the responsible AS, they suppose, so the responsible for those events are either on the old path or the new best path. There are several limitations from those approach. First, as we will say later, time is not the best criterion to identify those events. In fact, in the detection of burst of BGP updates, the big events are cannibalizing the small ones. In fact, all the events are merged into the flow of updates. And some events can be divided into several ones. So usually methods that clusterize updates based on burst cannot do that. And finally, we could see that with the detection of such events based on burst, we have to wait for the complete events to detect it. And as we will see in our methods, we can throw an alarm as soon as the event is detected. Okay, so I will show several assumptions that found our methodology now. So first, we collected BGP table dumps from 16 routers at Lynx. So this is the root views. It is at the root views monitoring point. So we collected one BGP table per day during 6 months. And what we can see in this figure is that so we compute the path from each source to each prefix, the path that is the most seen during the whole period. So we started with one month, then 2 months till 6 months. And what we can say, for example, if we can see that if you look at the x-axis, at the half of the x-axis, you can see that less than 2 or 3% of pairs source destination use this path more than half the period. I will try to get out this figure. If we look at the red one, at the right of the figure, we can see that 80% of the monitored pairs, they use the same AS path for the prefix during all the snapshot. So what we can say is that a router will preferentially use the same AS path during a long period to each prefix. So that is a strong assumption. Okay, now second assumptions. We saw this stability of BGP routing from routers to prefixes. Now we will try to see if AS paths to prefixes originated by the same AS are the same or not. So look at the red. One. It shows the number of prefixes originated by ASs. So we can say that, for example, 40% of ASs originate one prefix, and there is a small set of AS that originate so many prefixes. Hundreds to thousands of prefixes. Now, if we get a look on primary path, so the path that is most used from each router to each prefix to those prefixes of the same origin AS, we can see that 80% of origin AS, for 80% of origin AS, we've got the same AS path from the vantage point. And then, if we take into account the first neighbor of the origin AS, we try to know if a router will use the same AS path to the different prefix of an origin AS passing by the same neighbor of this origin AS. We can see that 95% of origin AS neighbor pairs, for those 95%, all monitoring points use the same path. So we can say that BGP routing seems to be more a neighbor-to-neighbor routing than a router-to-prefix routing. AS originates their prefixes, the prefixes is announced to the first neighbor, and then prefixes are routed the same way. In routing policies, usually administrator will not differentiate those prefixes originated by the same AS. So this is the second assumption of our method. So now we've got trees from origin AS to our collectors. So what we can say with that is if an event occurs at the originating AS, the primary path will be affected. So now we are thinking about trees from the originating AS. So those trees are trees of primary path. And now we try to look at the inter-arrival time of those updates at our monitoring points. So the red curve shows this inter-arrival time. What we can say about that? So the time, it's the time between two primary paths from the same tree are disappearing. So for half of the primary of the pairs monitored, it is under, we can say, 60 seconds. So I mean, if a primary path disappears, then for half the case, we will see another primary path disappear under 100 seconds. And the right part of the curve, we can say that there can be a long time between the disappearing of primary paths from one collecting point to another. So we decide to remove the detection of those disappearing at our monitoring points for different time thresholds. So for example, the green one. So we decide to forget. We've seen a primary path disappearing after 2 minutes. I mean, a primary path disappear, and if no other primary path disappear 2 minutes after, we decide to forget the fact that we seen this path disappear. And we can say with this assumption, with this removal, that the convergence time is about 100 seconds. So what we can say about that, if we see at a monitoring point a primary path disappear, then if we don't see after 100 seconds the same primary path, primary path disappear to the same prefix, then we can say the event is finished. So this will help us in the future. Okay, so here is the methodology. So given a set of BGP updates, this flow of BGP updates, we transform it into a set of unavailable primary path. So in fact, we don't keep updates that do not indicate primary path. We just keep trees from origin AS of the primary path that are disappeared. So so for example, we are in the state on the left. We've got 4 trees. One BGP updates arrive at a monitoring point, and this update tells that the primary path from AS1 to AS11 disappear. So we update the trees from the AS11. That's how we deal with the flow of BGP updates. Okay, now to deal with the detection of the responsible for from an AS, for each originating AS, we will compute the intersection of unavailable primary path. So for example, for the blue trees, we get only one link, one AS link, from AS11 to AS12. For the green part, we get the whole tree. And for the pink one, we get one link. So from those trees, we get those subtrees, that is the intersection. Then, from this reduction, we try to correlate the several trees to get more to the responsible AS. So, we decompose each subtree into AS links. So the green one was decomposed into 4 links. And then we try to identify AS links that appear in several trees. So we design a greedy heuristic that will select links that appear in the most unavailable primary path. So we detect those links, and then so we get the first link that appear the most in the most unavailable trees. Then we detect all the trees that can be explained from this link. We remove all these trees, and we compute the step another time. So at the end, so here we selected the first from ES11 to ES12. He appears in the most unavailable trees. Then we select the link between ES15 and ES32. So one more time, we remove trees that can be explained with these links. And then the last trees, the orange one, cannot be explained by a single link, so we select 3 ES links. So this set of 5 links can explain all the faded trees. So now we will try to improve the detection, and we will try to see if an AS can explain more those faded trees than links. So we split each of the link into 2 ASs, and then we try to identify an AS that can explain more than links. In this example, the AS15 can explain the fading of more trees than the links were. So in fact, we selected 2 responsible for all our faded trees. We get 2 events. The one first event is an event occurring at link from AS11 to AS12. So this link can explain 2 trees, 2 faded trees. Then with the AS15, we can explain the fading of the remaining trees. So what did we do, in fact? We have transformed the stream of updates into a stream of events. So we get the unavailable primary path, then the unavailable trees, and then we get the events. So those 2 events can explain all unavailable primary paths we've seen. And now, so this step is realized on real time, many times. It's a very quick step. And we decide to extract an event when we do not receive a new update of a tree after 2 minutes. So this fact was explained by the inter-arrival time of BGP updates we saw previously. So we try to validate this algorithm. So we took data at 16 routers at the root view peers at length. We get 37 million per prefix announcement. From those updates, 17% were indicating the unavailability of a primary path, and 18% were indicating the availability of a primary path. So from all this flow of updates, so 1 month of flow, we get 134,000 events. So that's that, and this represents only 60,000 distinct events. So now, this is not really validated for the moment. We take outage tickets from the AS 5511, so AS from France Telecom. and we look at all the failures and outage, and we try to validate if we can solve those failures with our algorithm. In fact, for half of the events we saw in the tickets were not seen in BGP data, but for all the events that can be seen in BGP data, we all identify them. And in fact, we also identify small events that can appear several times. So here is the curve that shows how many times an event occurs. So the same event, I mean the same link or the same AS explaining the fading of many trees. So we can see that 80% of events are seen only one time, but there are events that can be seen more than 6. There is one event that was seen 60,000 times. So that is recurring events that can never be seen with previous approach. So here is the summary of our contributions. So we designed a method to cope with this challenging problem of interdomain root cause analysis. So our aim was to inform network operations center that events has occurred as early as they can be detected. So our methodology really breaks with previous approach, as we do not use time thresholds to detect the events. Instead, we use topological consideration that we derive from real data. So the time information is only used to extract events. I mean, we extract an event when we do not see an available primary path after 2 minutes. And our ongoing job is to automate this tool and to present it to the community. So we hope this can help some operation center, and we hope to get feedback from the results to improve some of the limitations that can appear. And we have a final message about peering with public measuring points, is that the more you peer with those measuring points, it may benefit you. Thank you. And sorry for my Frenchy English.
Thank you, Mickael. Any questions?